All right, well, good afternoon, everyone. Welcome. Welcome to the 2021 Paul Zia Distinguished Lecture. We're so glad you're here. My name is Greg Coles. I'm a bridge engineer and project manager with AECOM and our North Carolina Transportation Group. It's been my honor for the past couple of years to be the co-chair of of our lecture series planning committee. And we're excited to feature the Samuel de Champlain Bridge as this year's topic. Can't wait to introduce our two speakers in just a few minutes. For over 20 years, the Paul Zia Distinguished Lecture Series has featured expert structural engineers, architects, contractors, and their landmark civil engineering projects across the world. The series honors Dr. Paul Zia, Distinguished Professor Emeritus at NC State, and his contributions to the knowledge and practice of structural engineering across the world. We're honored to have him and his family join us at Stewart Theater today. We're so excited to have so many of you join us online this afternoon and to be able to host a few students and faculty here on campus at Stewart Theater. On behalf of the university, please join me in giving a warm Wolfpack welcome to our keynote speakers, Dr. Marwan Nader and Mr. Guy Mayotte. Thank you both for giving of your time to support NC State and our local engineering community. An event like this cannot happen without sponsors. We are so thankful to have so many sponsors return each year and to have new sponsors joining us this year to support the mission of the lecture series. At this time, please turn your attention to the screen and help me acknowledge our sponsors for this year. Our signature sponsors are Dr. Darren Holt and WSP. I'd also like to thank our gold, silver, and bronze level sponsors. Please know that your contributions go much further than simply making today's event happen. They fund scholarships, they create experiences for civil engineering students, and I've got slides that want to jump ahead on their own. Sorry about that. And beyond that, they provide, or this lecture series has provided countless inspiration to students as they begin their careers. So again, thank you. Please join me in thanking the sponsors for this year. So on the screen, as it's wanted to jump to so quickly, you'll see the agenda for today's program. At any time during the program today, if you're joining online, you can submit a question through the Q&A box. We're going to be moderating those questions, and near the end of the program, we'll present those to the speakers. If you're here in Stewart today, please save your questions to the end. We have microphones at the front, and we'll give you a chance to ask them. For all engineers in attendance, 2 PDHs are available, and they will be emailed to you based on the email that you signed up with in about 2 weeks. If you're here today, we'll have some forms for you to take on your way out. Again, welcome. I hope you enjoy today's event. At this time, please welcome Head of NC State's Department of Civil Construction and Environmental Engineering, Dr. Mort Barlaz.
Good afternoon and welcome. I want to thank everybody for joining us virtually for this, the 20th annual Paul Zia Distinguished Lecture. I'm thrilled to have such a large group of distinguished architects, engineers, contractors, students, and faculty here. In fact, as of this morning, there were 686 people registered online, which is just fantastic. We're here today, as Greg mentioned, to honor a very special professor, Dr. Paul Zia, who has contributed greatly to the field of civil engineering and has influenced the careers of so many individuals. The Paul Zia Lecture Series was created not only to honor Dr. Zia, but also with the specific purpose of providing a link for existing students to the real world of engineering practice. Through the years, the lecture has evolved into an opportunity for students, researchers, practitioners, and even the general public to learn about exciting projects from around the world. In fact, I can say personally, as an environmental guy, I've learned a tremendous amount about civil infrastructure from personally attending these lectures over the last 12 years or so. Of course, as Greg mentioned, events like this require tremendous financial support, and you've seen the slides acknowledging our gold, silver, and bronze sponsors. And I just want to add my sincere thank you and appreciation to these sponsors. And as Greg mentioned, they go beyond this lecture to supporting some scholarships and educational enhancements for students studying various aspects of structural engineering. I also want to extend my thanks to the ZIA committee. As you can imagine, events like this don't just happen. They happen because there's a committee of volunteers that has been working over a year ahead of time on this year's lecture. And I really want to express my appreciation to all the members of the ZIA committee for their tireless work. And of course, that makes, in the era of COVID, making their job even harder. So maybe we could just take a moment to thank the ZIA committee. So before passing the mic to Dr. Gilligan, it's my sincere pleasure to recognize 4 outstanding PhD students with awards that are sponsored by the ZIA Symposium. And 2 of our honorees are here in person, and 2 are remote, and I've just elected to go in alphabetical order. Our first recipient is Laura Elizabeth Dalton, who is currently in Finland on a Fulbright scholarship as part of her PhD. She's advised by Dr. Mopur Gas, and the overall goal of her research is to study and understand multi-phase transport in porous media. She's particularly interested in understanding and manipulating chemical and physical processes that occur during reactive multi-phase transport in both engineered, such as cementitious material, and natural porous materials. The broader impacts of her work include carbon capture and storage, as well carbon capture and storage well integrity, carbon dioxide sequestration, and the development of carbon sequestering cementitious materials. So Laura, I guess it's a little bit after 9 at night there, probably dark, but our congratulations to you. Our second recipient, who I believe is here, is Tubin Roy. Come on up. Dr. Roy utilized advanced computational approaches to develop a new method to estimate the stiffness of human arteries using non-invasive sound imaging techniques. Arterial stiffness is an early indicator of cardiovascular disease, and his method is currently being tested on real patients at the Mayo Clinic. So congratulations to Dr. Roy. Our next recipient, who is also here, is Pragya Vaishnaw. Come on up if you're here. Great. Pragya developed a novel methodology for system-level probabilistic risk assessment. This methodology allows implementation of risk-informed decision-making tools in digital twins for advanced nuclear reactors. Her work on a computationally efficient Bayesian approach has a lot of promise to change the current state of the practice. She has also served as an excellent mentor for master's and undergraduate students. Please join me in congratulating Pragya. And our last recipient does what universities do best. We take our best people and then we move them on to the next thing. Dr. Francisco Valverde, Sr., completed his doctorate with Dr. Mo Porgas. He developed new methods for carbon sequestration in Portland cement-based materials during the material processing stage by converting hydration byproducts to calcium carbonate. His research showed that carbon sequestration in Portland cement-based materials can enhance their durability by converting unstable phases to calcium carbonate, which in turn reduces the need for repair and replacement. So congratulations to Francisco. And I neglected to mention that Pragya is advised by Dr. Abhinav Gupta, and Tuhan Roy is advised by Dr. Murthy Gudati. And with that, I would like to welcome Distinguished University Professor and Senior Associate Dean of the College of Engineering, Dr. John Gilligan. I'm proud that as a department and as a College of Engineering, we are internationally recognized for excellence in research, education, and outreach programs. And please welcome Dr. Gilligan.
Well, thank you very much, Mort. Appreciate the welcome, and thank you all for being here. It's an outstanding event. This is the most excited I've been in a while. I haven't been in front of this many people in a year and a half. So here in the Stewart Theater, there's probably 60, 70 people here, something like that, just to give you an idea of how things are opening up back here on campus. About 80% of our classes are face-to-face now, which is, again, very exciting. All the research is moving ahead in person. And so we hope things are getting back to a little bit like normal. And I hope they are where you are as well. So Mort, thank you again. I'm here for Louis Martin Vega, the Dean of Engineering. He couldn't be here this afternoon. So it's so exciting, as I said, the wonderful sponsors, we thank them, the speakers that are here. It's an outstanding program. I've been attending this over the years. This is the premier event, I think you could say, as a seminar-sponsored event in the College of Engineering. And it's led a great example for what other departments and other disciplines can do to highlight what NC State does and the importance of what we do and the accomplishments of NC State in general. The College of Engineering is very proud of this event and the kinds of things that we've accomplished over the years. Right now, we're about almost 11,000 students in the College of Engineering and $200 million in research, sponsored research activities. This puts us in the top 10, really, in the country in terms of graduates and sponsored research. So you're at the very highest levels of accomplishment associated with all of engineering disciplines. Just this past year, we were awarded 2 more NSF research centers here on campus. Very excited about that. I don't think any other university in the country has had 2 awarded in the same year. So again, we're on the map. The other obvious thing that's happening here in the College of Engineering is the opening of Fitzwillard Hall, where Mort and his colleagues in civil engineering are now located. So that's a very exciting transition, moving from Mann Hall out to the Centennial campus. We hope that you can visit as soon as you possibly can the campus and see the wonderful atmosphere, the way the students love the new Fitzwillard Hall, and how faculty and others are transitioning in that process. There's going to be a grand opening October 29th. It was supposed to be last year, but obviously we waited till this year. So as many as possibly can, we hope that you can attend that event. I wanted to mention something personal about Dr. Zia. Paul, I remember when I arrived here on campus in the early 1980s as a new faculty member, I served on committees with you. You were the department head at the time, I believe, in civil engineering. And I can remember being so impressed with Paul, Dr. Zia, his wisdom, how smart he was, but how nice he was. That's just his personality. He reached out to me in another department and really had a strong impression on me that I appreciate even to this day. And I couldn't believe he was a department head. It was really quite an extraordinary experience. That was just your personality and the way that you reached out to all faculty at all levels and really made a difference here in the College of Engineering. So it's fitting that we honor you with this lecture over the years. It's something that's fits your personality, the accomplishments that you've had in your life and your professional career. It's really meant a lot to everybody. We hope that you're going to enjoy, everybody out there enjoy the lecture today. And thank you, Paul, and your family for being here as well. We really appreciate it. Thank you very much. And now I think we have a video from you, Paul, I believe.
Good afternoon. I appreciate this opportunity to make a few remarks. First, I would like to extend my warm welcome to all of you, the students and the faculty who are here in person attending the lecture, and also to all of those who are attending a lecture virtually. It's hard to believe this is the 20th annual lecture. When the lecture was initially initiated about 19 years ago, it had a relatively modest beginning. It was almost like a seminar. But about 15 years ago, a group of our Loyola alumni and friends saw the opportunity to transform this lecture to showcase some of the world's most critical infrastructures that's created by the civil engineering professional. The lecture certainly has benefited the students' educational experience, and it demonstrates to the students the complexity of creating such structures, as well as illustrate its economic, social, cultural impacts on society. Furthermore, the students also benefit from a personal contact with the speakers, as well as the other professionals. Again, my thanks to the sponsored speakers. I do hope that series will flourish in the years to come. Thank you again.
Good afternoon, everyone. My name is Santiago Aguilar, and I'm a senior lead consultant responsible for the design of a variety of bridge and transportation projects here in the United States and in Southeast United States and the West Coast at WSP. I'm a graduate of Michigan Technological University, Department of Civil and Environmental Engineering. and I'm very honored to serve in the ZIA committee. As a matter of fact, my graduate thesis was based partly on Dr. Zia's method for estimating price losses, which makes this lecture of very great significance to me. I would like to acknowledge all the members of the ZIA committee for making this lecture a reality. This year, the committee worked proficiently and diligently on making the lecture a hybrid event so that we can continue a 19-year tradition of honoring Dr. Zia and supporting the department. Today, we have a great audience here at Stewart Theater, as well as a great audience virtually across the United States. On behalf of WSP, I would like to thank you. I would like to thank the committee for giving us the opportunity to be this year's presenting sponsor. At WSP, we are the sum of our collective passion, vision, and expertise. Discover the people, purpose, and stories that are helping us shape the organization we are today and the one that we are designing for the future. At WSP, we work on very exciting projects across multiple disciplines in the United States and the world. We do our best to meet our clients' expectations and provide a wide variety of services with a diverse team of experts in transportation, environmental sciences, energy, healthcare, high-rise buildings, aerospace, waterfront structures, among other areas of expertise. For more information, I encourage you to refer to www.wsp.com. At this time, I would like to introduce this year's ZIA committee speakers, Mr. Guy Melot and Dr. Marwan Nader. Mr. Guy Melot is the chief engineer for the Samuel de Champlain Bridge Corridor project at Infrastructure Canada. For over 30 years, Guy's career has focused on the design, inspection, and rehabilitation of bridges, including Montreal's most important bridges and the Alex Bridge in Vancouver, once the world's longest span cable-stayed bridge. His last 9 years have been devoted to the Samuel de Champlain Bridge. He contributed to all phases of this project's delivery, including pre-feasibility studies, preliminary engineering, procurement documentation, the design-build phase, and the design and construction to incorporate a light rail transit system on the bridge. A recipient of numerous industry awards and recognitions, Guy is a member of the Quebec Order of Engineers, a fellow of the Canadian Society for Civil Engineering, and a fellow of the Engineering Institute of Canada. Tonight's second speaker is Dr. Marwan Nader. Dr. Marwan Nader is a senior vice president at TY Lin International and is the engineer of record and design manager of the Samuel de Champlain Bridge. His career spans over 3 decades of long-span bridge design and construction. His global bridge expertise includes the San Francisco-Oakland Bay Bridge, the world's longest self-anchored suspension bridge located in a seismic zone, and the Bataan-Cavite Interlink Bridge project in the Philippines, which consists of 2 cable-stayed bridges which span up to 2,900 feet. A recipient of the ASCE's Arthur Wellington Award, Marwan was recently appointed to UC Berkeley's Civil and Environmental Engineering Advisory Council and is a distinguished alumnus of this university. We are very honored to have you both here at Stewart Theater. Let's welcome our speaker with a round of applause.
So thank you for that kind introduction. Special thanks to the organizing committee. It's been really something to organize through the COVID pandemic coming in from Canada. Very, very knowledgeable and glad that Greg was there to help me out. I felt almost like a rock star. He was driving me around town, picking up at the hotel, bringing me to clinics to find a test, to be able to get back home. So thanks a lot, Greg, very gracious host. On behalf of Maran Nader and myself, it's a great pleasure to be able to give this presentation on the delivery of the Samuel Champlain Bridge. For me personally, it's really nice to be here in person with you. It's the first time I was able to travel in over a year and a half. So I hope you enjoy the presentation. So the presentation will be given in two parts. I'll cover the first part where I'll talk about some of the background and context. I'll explain the need to intervene. I'll talk about the pre-feasibility study and the business case. I'll talk about the architectural quality and vision, which is the community's expectation for this signature bridge. I'll mention the durability objectives, and you'll understand why I'll talk about durability. I'll say some few words on the design requirements, and I'll give some information on the project's cost and schedule. And then Marwan will cover part two, where he'll talk about the governing loads, design of approach structures, design of the cable stay bridge, the fabrication, construction, and the main takeaways. Now, the project is located in Montreal, Canada. Montreal itself is on an island. There's a neighboring island, which is called Nuns Island, or Ile des Sars, at the end of that orange line. And to the south of the river, on the south shore, is the city of Brossard. Now, Montreal is located about an hour's drive from the Canada-US border. These pictures here show the original bridge. The original bridge consists of three sections: the steel cantilever truss section and its flanking deck girder spans, truss spans. It spans over the International St. Lawrence Seaway. It also has the approach spans, east and west, which are made of pre-stressed post-tension concrete girders. And you can see an image of that to the image on your left. It is really the deteriorating condition of the approach span girders which was driving the need to replace the bridge. The bridge is one of Canada's most important bridges. It links the island of Montreal to the South Shore, and it plays a very vital role in the Canadian economy. It's estimated that 50 million vehicles and 11 million in public transit use the bridge every year. It's responsible for about 20 billion in Canada-US trade, and it crosses over the International St. Lawrence Seaway that links the Atlantic Ocean to the Great Lake regions. And you can see a picture in the bottom there of the bridge over the seaway. If you look at the image above, you'll see a reserved bus lane. That was actually implemented it's a contour lane. It was implemented at the end of the 70s. I was a student of McGill. I did my undergraduate and graduate studies there. I took that bus for 5 years. Never would I have expected that one day I would be involved in the replacement of this structure. Heck, it was only 17 years old when I was taking the bus across the bridge. But I would also never have anticipated that bus system would last until the bridge was actually put out of service. So when you talk about time is relative. Temporary measures, sometimes they can last longer than we expect. And sometimes, if we're not careful, permanent solutions can last shorter than we can expect. So the construction of the original bridge began between '59 and completed in 1962. We have a few pictures here that shows construction of one of the piers. It's a gravity-based pier in the river. A picture here showing construction on the precast yard at the site, constructing one of the precast post-tension girders. I must say at the time this was probably the largest pre-stressed precast concrete project in North America at the time. You can see here erection of the cantilever truss over the seaway. The seaway opened in 1959, so the bridge was actually built over live seaway navigation, a bit similar to what had to be done for the construction of the new Samuel Champlain Bridge. And you see here a picture showing the erection of the precast post-tension girders using an erection launching truss. So the bridge was opened in 1962. There were signs of problems as early as 1987, about 24 years after opening, where we had to repair the first repairs of the concrete girders. About 30 years after opening, the entire deck of the steel crossing over the shipping channel had to be entirely replaced. It was replaced by a steel orthotropic deck. You can see in the underside of the deck here is a picture I took way back in the 90s. You can see a whole bunch of orange patches. Those are actually formworks that were left in place following patch repairs, and I think you could say there's probably more patches than there is sound concrete. In September 2010, the federal government undertakes an pre-feasibility study for a replacement crossing. And in October 2011, the government announces the replacement of the bridge by a new bridge. About the same time, a consulting firm produced a report that said the deficiencies and associated risks are such that the Champlain Bridge should be replaced by a new crossing, and an expedited process to accomplish this should be implemented. About 2 years later, another report by another consulting firm says the bridge is quickly approaching the end of its service useful life. As such, replacement of the bridge must be expedited to ensure continuous use of the crossing. So we essentially went from the word should to the word must. So by the time I guess the government heard the message, in September 2013, the government announces that it will accelerate replacement. We were talking about delivery in 2018. About a month after that, the owner of the bridge, the Jacques Cartier Champlain Bridges Incorporated, had to close a traffic lane after the appearance of a flexural crack at mid-span of an inch girder. A few months later, we installed an emergency above-deck super beam. This was pre-purchased as an emergency response plan, or almost an insurance policy. Never expected to have to use it, but it served that purpose. And then it was replaced by an under-deck emergency truss. That led to a request for qualification and eventually a request for proposals in July of 2014. This image shows a typical approach span. You can appreciate the 7 girders. There are 50 spans, so there are 350 individual girders. The original Champlain Bridge had an unusual configuration. There's really no deck to the system, and the wheel loads are carried directly on the top flange of the girders. There are infill panels between the girders. There's no passive reinforcement between the flanges and the infill panels. Sorry. Everything is held together by transverse post-tension throughout the slab, which makes a highly integrated system and makes the individual replacement of a girder practically impossible. If I had to say what are the 3 main reasons for the premature deterioration of the bridge, I would have to say that when the bridge was being designed, it wasn't anticipated that salts would be used during the winter period. By the time the bridge was open to traffic, salting of the roads had become a standard practice. The second element is that this was technology that was imported from Europe, France, and Belgium. Some of the detailing, especially for the post-tensioning ducts, was not well appropriate for Montreal's climate, and there was also issues regarding the quality of the grouting of the ducts. And the third reason is a poor drainage system, or should I say the total lack of a drainage system. Salt-laden water was just allowed to trickle through openings in the railing system in the curb, trickle down the fascia of the girders. Of course, this led to chloride ion penetration through the concrete cover, attacking first the stirrups, eventually reaching the steel post-tensioning ducts, corroding through those, and then eventually reaching the steel pre-stressing wire. Of course, when the steel corrodes, it expands, and you get spalling of this nature. In certain cases, we had spallings on both sides of the webs. The webs were relatively thin. We did install a drainage system about 30 years after opening, but by then the chlorides had already penetrated and the concrete had the cancer in it. This shows a picture of one of the girders. You can appreciate the extent of damage. The standard practice would be to chip spalling concrete, see the condition of the girders, count the number of wires that were lost. We did apply external longitudinal post-tension to compensate to a certain degree. And this gives you a picture of the extent of damage. There are simple spans, so all the cables are bunched up at mid-span in the lower flange. The 24 cables, and I think this picture there was probably a loss of 7 of the 24 cables at mid-span. That led to some, the initial approach was just to add external longitudinal post tensioning. We did quite a bit of that. Later on, we started to add queen posts to increase both the flexural and shear capacity, to eventually the installation of supporting trusses along all exterior girders. In the years near the end of the life of the bridge, we had spent about $300 million over a 6-year period just keeping the bridge alive until we can get the new bridge in place. This is the interesting page. It's taken from the original proposal that was issued in the late 50s, and it says, "Our bid has been prepared under the high authority of Eugene Fresnay." For some of you younger engineers, Eugene Fresnay is actually the inventor of pre-stressed concrete. It goes on to say, "A pre-stressed concrete structure, with the possible exception of the railing, requires practically no maintenance." So what can you say to such a bold statement 60 years after the fact? Well, you can say that experience is something you get just after you need it. You can say that structures and materials will never fail. They will always behave according to well-defined laws of physics, so it's always a human failure. If you want to put a more positive spin to it, you can say that everything is obvious once you know the answer. So we did pre-feasibility studies. We did look at a tunnel option. In the case, you have a profile here showing a bored tunnel. Of course, a bored tunnel, you would have to have a certain depth below the riverbed, probably equal at least to the diameter of the tunnel. In this case, we would not be able to connect or have an exchange to the Nuns Island there. We could have a large elevator shaft for public transit, but we would actually miss interconnection with the island there. Here you have two images. The upper portion shows a tunnel configuration that could have been built within a cofferdam. It would have been a very wide tunnel at 59 meters wide. The bored tunnels would have been two twin tunnels bored at 17-meter diameter. At the time, that was probably at the limit of the tunnel boring machinery technology at the time. In both cases, they both had allowance for a mass transit system. So the tunnel option was discarded in favor of a bridge for the main reasons were we had estimated the cost of a tunnel to be 1.5 times more than a bridge. It would be more difficult to connect to the existing infrastructure. The infrastructure at both ends was already built and we wanted to connect to it. There would be significant environmental impacts. What do we do with all the material that we've taken boring the tunnel, but also if we had to build within cofferdams. There was also a big issue regarding accommodating the hazardous materials through the tunnel. Those are always typically a big problem for tunnels. We did look at different bridge configurations. The lower image probably shows a more structurally efficient system with V-shaped piers and variable inertia girders. A more iconic solution that was looked at was cable-stayed bridges. Actually, it's two cable-stayed bridges placed side by side with the main towers offset one to the other. So we ended up in the pre-feasibility saying that, while the bridge option was more advantageous than the tunnel, we had recommended 6 lanes with 2 additional lanes for a dedicated mass transit system. We had recommended that the bridge be constructed immediately downstream of the existing one to allow easy connection to the existing built infrastructure. We had looked at various bridge types, but for the approach spans, we're typically looking at 80-meter spans in steel or concrete and a variable depth girder or a cable-stayed bridge to cross over the main span over the seaway. And this pre-feasibility study served as the basis or the main inputs for the federal environmental assessment. We then moved on to the business case where we took the initial options for bridge. We added 8 new options, did a pre-screening process, and to land to what we called a preferred alternative. And the preferred alternative was just basically to help further develop the business case, the funding level, scoping of the project. As part of the business case, we looked at different options, a variable depth box girder arrangement. We looked at arch bridge. We looked at truss bridges with V-shaped piers. We looked at extradose bridges, and we also looked at long span cable-stayed bridges with back-to-back long span bridges. We also had to look at what are the corridor configurations. So we had looked at 2 corridors. We had looked at double-decker, where the upper deck would carry highway loading and the lower deck mass transit. we settled on a 3-corridor system with the central corridor reserved for mass transit. As part of the costing, a consultant was working for the owner, Arup Canada, had produced numbers and costing different options. I actually took their numbers and normalized it with one of the cost figures and plotted on this curve that I had from my own information that I had on my hand. I think we were working from the same graph because the curves, the dots almost align up quite well to the curve. What it shows is that for the span of about 215 to 240 meters, which is the span that we have, there's a whole variety of bridge configurations. It can be a cable stay bridge, it can be an arch bridge, it can be a variable depth box girder. It also shows us that at 80 meter span, that's kind of what is recommended for constant depth box girder, and essentially what we ended up using on the bridge. It also tells us that, you know, pop in and say, well, why don't we just build, you know, long span bridges, and those look interesting. Well, as you get the longer and longer spans, once you start getting past the 300 meter spans, well, the cost starts to rise exponentially. So we ended up with a 3-corridor system. We're looking at box girders either 65 to 80 meters in concrete and 80 to 100 meters in steel. For the business case, we looked at an Extros bridge with for the main span, and we were looking at vertical cable planes, looking at a single level bridge, and again, the central corridor would be reserved for mass transit. So this shows the configuration of the new Samuel de Champlain Bridge. The 3 main sections, again, the west approach, which is about 2 kilometers long, or what's that, 6,700 feet, the cable stayed bridge section, and the east approach. The bridge, as you can see, is slightly curved in plan view. Now, we'll be talking here today about the Samuel de Champlain Bridge, the main bridge, but the project is more than just the main bridge. It's an entire corridor project. We ended up widening, reconstructing the highway and widening it from 4 lanes to 6 lanes. Constructed a new Nuns Island Bridge. It's a low-level crossing about 500 meters long. Work on the Nuns Island, where right now there's a train station that's being built right in the middle of the 2 highway corridors. The main crossing, the Samuel de Champlain Bridge, and works on the South Shore approach to connect to the existing infrastructure. This is the architectural rendering that was developed prior to launching of the project. You can appreciate again the navigation in the St. Lawrence Seaway. There's one longer span over the Highway 132. There was a requirement that the depth of the bridge be the constant from abutment to abutment. So there were some challenges in developing that longer span, something on the order of 108 meter long span. That was a challenge for the design build team. Of course, you know, the challenge was finding a balance between the architectural features of the bridge, construction feasibility, and design for durability. And I think Marwan would say, well, we could have done more to make it easier to build. There's a lot of details in there which are not really, you know, not the first thing a structural engineer would think about. We also wanted to preserve the architectural vision. We were working closely with the architects. We ended up producing what we call definition design drawings that laid out the exact shape of the structure, but we did give full freedom to the design build team as to the choice of materials and also the internal configuration of the structure. There was a high expectation from the community for an iconic bridge, a bridge that would be easily recognizable. It is the gateway to Montreal, and you know, we think we achieved that objective by having an asymmetrical cable-stayed bridge. We have very distinctive W-shaped pier caps, and you'll see that in a few minutes. We have a curved bridge, and we have a sophisticated architectural lighting system, and I'll show you a picture of that at the end of the presentation. When the Minister of Transport of Canada announced the project or unveiled the project to the public, first thing he said is, what you see is what you get. He wanted to make sure that what we build would be actually what he announced. In this picture here, you can appreciate the 3-corridor system. You can appreciate the fact that the bridge is slightly curved in plan view, and you can appreciate the distinctive shape of the pier caps. Right here, we're underneath the cable stay bridge portion and looking towards the the island of Montreal. You can see that the corridors are independent for the approaches, but as we get to the cable stay bridges, the corridors are interconnected by cross beams. The architects, you know, a really engineered solution from just a structural perspective would have been a straight bridge. There would have been columns under each of the corridors. And one of the first things the architect said, you know, if you make a slight curve in the bridge alignment, there will be much better user experience as they cross over the bridge. They'll have a changing view of the spectacular Montreal skyline. So they were really favorable to a slight curve in plan. The other thing he said is, you know, if you have too many columns in the river, when you look at the bridge from a skew angle, the only thing you're going to see is a force of columns. So they really wanted to lighten up the number of columns in the river. I said we had to preserve the architectural vision. So this is the owners and the architect's vision. We asked that the design build team produce their own rendering just to demonstrate that their design would preserve that vision. And you can see it's pretty well matched there. And this is the actual piers constructed with a similar view from underneath the bridge. In terms of the project requirements, in certain areas we were very prescriptive, so it was a combination of prescriptive requirements and also performance-based requirements. We took the standard truck model that's used for typical bridges in Canada. We increased that by 10% to account for the extended design life. We designed the central corridor for either buses, in case the buses would equivalent to a truck loading. And we also allowed for a light rail train, and we based the light rail train loading and the design of that on Eurocode, and I'll say a few words about that later. We knew that it was anticipated on day one there would be buses running down the central corridor, but we knew at one point they might want to put a rail system down the middle. So we built the bridge with extra wide shoulders so we could divert the buses to the shoulders to free up the corridor, and so they can put rail. And that was actually a very wise choice, because about a year after we started building the project, the government of Quebec informed us that they are implementing a rail system, and that's actually being implemented as we speak. We did have a requirement for a special truck loading. We were basing essentially a special truck that's been used by Caltrans. It's a very long truck, about 2.5 times the standard truck model. You can see here the configuration for carrying essentially 2 cords carrying 4 lanes of traffic, and there is a multi-use path on one side. Special truck here. The requirement was that the design life for all non-replaceable components would be 125 years. We imposed a mandatory use of stainless steel reinforcement for 100% of the deck slab and all other strategic locations. There was a requirement to undertake time-to-corrosion modeling using state-of-the-art modeling techniques. Of course, if the bridge has an extended design life, there's a requirement for fatigue evaluation over that extended design life, both for the steel components but also for the reinforcement in the deck slab. We did require reserve capacity for structure design, so we can allow for the replacement of a stay, but also if we lost multiple stays under an extreme event. For non-replaceable components, they had a 125-year design life, so that included the foundation units, the piles, the pier caps, the footings, the infrastructure, the piers, the abutments, and the main span tower, as well as the superstructure, but it also included that the deck slab also has a 125-year design life. The other components have to be replaceable, which means that you have to anticipate that one day they will be replaced, and you have to favor techniques to allow that replacement. The stays are one of the particular animals in that group. It has a 65-year design life, so that means at the end of the concession, the stays would have gone through about half of their design life, so we have special requirements to investigate the stays before the structure is handed back to the government. We impose a limitation on the number of expansion joints. There are 8 expansion joints on the new bridge. That compares to 57 on the original bridge. Some would say that an expansion joint is something that leaks or something that will leak in the future. We wanted to cut down on those number of joints. Of course, if you have less joints in the Montreal thermal movement, the joints accommodate quite a bit of movement, the joints become more complicated, more extensive. They say that a bridge that is well maintained is a bridge that is easily accessible. We impose shuttles in the box girders. We have an elevator in the tower legs for the main span tower. There's a cable, a traveler for the main span and the back span. all the hollow piers and the pier caps are equipped with ladders and staircases. There's a comprehensive structural health monitoring system. We have something like 400 instruments on the bridge to monitor the health of the structure. We impose mitigation measures against stray currents and induced currents by having a good grounding system, but also stray current collection cables. That's very important considering that we are running an electrified rail system on the bridge. And there are handback requirements that's to ensure that the bridge is handed back to the government after 30 years in a good condition. We were quite restrictive on the concrete materials. We required a high-performance concrete, a very relatively low water to cementitious material ratio of 0.32. We required the use of ternary cements or blended cements to help encourage the long-term durability properties over the strength properties. Requirements on chloride ion penetration values. We also required, as I mentioned, to demonstrate the service life using general principles and probabilistic methods of the Bolton 34, which is a model code for service life design. Design built to match use Stadium software, which is developed by a company in the province of Quebec. And we did require special mixes to account for abrasion loss, as the piers in the river will be subject to ice rubbing. In terms of we wanted a bridge that would, be world-class, best practice for in the international stage. That was a challenge. We ended up combining several codes. Some codes are more advanced than others. There's also potential overlap between the codes. Codes get updated frequently. In the case of the Champlain Bridge, we actually went through 3 code revisions for the Canadian Bridge Code. We wanted to satisfy a 125-year design life. Most of the Canadian code at least is calibrated for 75-year design lives. We wanted to be state-of-the-art in terms of seismic provisions, and in fact we ended up adopting a draft version of the new Canadian Bridge Code, which was going to include a performance-based design. So again, we didn't want to be obsolete from a design perspective on the day the bridge was open, so we ended up integrating the new version of the code as the seismic requirements. And there was a challenge in combining highway with rail traffic, so we had to be very, innovative or thoughtful on that aspect. So we ended up, to meet these challenges, ended up listing a whole bunch of standards and giving their order of precedence. We established a time frame for which the codes would be effective. So in our case, I think it was March 2014. So that was the code to which everything had to be designed, and the project would be delivered on the basis of that reference code. We did specify special loading combinations, and I'll show you an example later. We did say that in case of a conflict between codes, because there's often some conflicts between codes, that it was the Canadian Highway Bridge Design Code that would be the governing code. And we also required that the design team, develop right off the bat their design basis report, which indicated how they were going to manage all these code requirements and to make it clear up front that this is the basis for their design, which was quite helpful. We referred to a number of international standards. The Canadian Highway Bridge Design Code, the Ministry of Transportation has their own guidelines and practices. Did refer to AASHTO in certain instances. We did require European codes and British standards, especially for the design of the large steel-plated structures. Federal Highways Administration, American Welding Standards, Canadian Welding Board. Of interest is the PTI recommendations for stay cables, but also PTI recommendations for grouting of PT ducts, which, as I said before, was one of the sources of problems on the original bridge. FIB bulletin, which I mentioned, and we also have generators in the abutments and so fire suppression systems. So even referred to NFPA standards. The chart on the bottom, is part of the design basis, and it's the designer's interpretation of how they're going to apply our requirements and in reference to different code requirements. In terms of seismicity, as I mentioned, we did incorporate the latest standards for seismic design. The figure on the right shows the various earthquake magnitudes around the Montreal area over the past 400 years. People always ask, what is the magnitude of earthquake that a bridge can withstand? Well, you can't just talk about magnitude, you have to talk about distance from the site. But just to give you an indication, if you look at a 200-kilometer ring around Montreal, for a 1 in 2,500 year event, you're talking about a magnitude 6.5. And if you're looking at a 1 in 1,000 year event, that's a magnitude of 6.1 that could occur within that radius of 200 kilometers. We asked the bridge be designed using performance-based, but a lifeline bridge. So what does a lifeline bridge mean? Well, it means under a 1 in 1,000 year event, we need immediate service. So the bridge is fully serviceable for regular traffic, and for the light rail transit, there's no reduction in service, essentially saying it's business as normal. For a more severe earthquake, a 1 in 2,500 year event, it has to be usable for emergency traffic. At least 50% of the lanes remain operation, and the light rail transit system has to still be able to be used, but it would be used at reduced speed. It also implies that the bridge has to suffer damage, but the damage has to be repairable. So we do allow some inelastic behavior under the large seismic event. The structure has to retain 90% of its seismic capacity for aftershocks. You don't expect any residual significant settlement of main structures, and we don't expect a permanent offset of the structures. So this requires to limit the strain in the material. Essentially, we allowed the structure to be designed elastically, but there would be a requirement to increase and the design team did adopt a essentially elastic design, but there was a requirement to increase the seismic forces by 30%. I said challenge was the light rail loading. We didn't know at the time what would be the exact type of light rail system. We didn't know if there'd be a light rail on day one or in 30 years or never. We ended up adopting a Eurocode loading, and so this is just the model of the loading. But of course, if you have rail traffic, then fatigue becomes quite a significant issue. And so we ended up prescribing the frequency of different axle loads from the train model. We had very good foresight, and so as I said, we planned that one day we'd want to perhaps install a rail system. And as I said, we made the shoulders wide enough so we could divert the buses to the shoulders to free up the central corridor, and that's what's being done right now. The bridge at the cable stayed is very wide at 60.2 meters. I think it may be the widest bridge in the world that's supported by only 2 cable planes, so there are challenges there as well. Just one example here, as I mentioned, the trains will be running at frequency 20 hours a day in principle, 90 seconds between the trains. So we imposed that the trains be always considered to be on the bridge, and there'd be no reduction with the lane combinations. And we had an example here. We ended up modifying the standard table in the code to allow for a light rail train loading in the various combinations. About 4 years after we launched our project, NCHRP came out with some guidelines of how to combine highway loading with rail loading, and so that might be a useful tool, but it came out a bit late for us. But it's a trend now. You'll see more light rail perhaps with the bridge design. So if I get into the actual delivery of the project, well, a contract was awarded on June 19, 2015. The bridge was open to traffic on July 1st, 2019. It was Canada Day, a $4.2 billion PPP project, about $2.2 billion for the design build component. And as I mentioned, the bridge is the cornerstone or the key element of the project. T.Y. Lin is the managing director for the design joint venture. They're also the cable stayed bridge engineer of record. In terms of cost, as I mentioned, $4.2 billion. About $2.2 billion is for the DB cost. The balance is for the operation, maintenance, and rehabilitation, and includes some financing over the 30-year period. The main takeaway from this one is the fact that the bridge was fast-tracked. There was a 48-month period for schedule from design to construction. 48-month period for a bridge of this size is quite spectacular. Marwan will be talking about accelerated bridge construction. We also have to keep in mind that we went from a decision to replace the bridge in 2011 to a delivery of a bridge some 8 years later. So there was also fast tracking in the procurement phase. I think it just shows if you had to replace a bridge of that size, it is possible, and it'll be, I think, an example of what can be done if there's really a need to deliver it quickly, which in our case was absolutely the case. I'd like to say that this image is in honor of the U.S. flag, the red, white, and blue. It just shows an example of the sophisticated lighting system we have on the bridge. It actually was taken during the Montreal Canadiens run to the Stanley Cup. They made it to the finals and kind of got excitement with the crowd. And so we were able to light up the bridge in the color of our team. So with that, we'll have a video, and then I'll pass the puck on to Marwan.
All right. So I am coming to you from San Francisco. I'll now cover the latter second part of the presentation now that Guy has described to us the process by which the owner and the client put the performance specifications for a replacement of the Champlain Bridge. And the portion that I'll cover is how we actually, as a P3, or more importantly, as a design builder, satisfied the requirements of this very aggressive schedule and took all the requirements in terms of performance into an actual design that ultimately got fabricated and delivered. As Guy mentioned, the schedule was very aggressive, 48 months. So we basically, what I'm about to go over in the next 35 minutes or so is to describe the process by which the designer, the contractor, and ultimately the operator from the P3 side, the equity, work together to deliver this project. I'll start first by covering the governing loads and the hazards, followed by the design of the approach structure, which is the majority of the project, MBSL project or the Champlain Bridge, and the signature span, the cable stay bridge. And I'll touch on the fabrication components and the construction and key takeaways. The first key to take into this is that it's a 125-year design life, and you need to work with severe winters. And in that, you have to look at exposure to de-icing salts. It's a very aggressive environment in terms of corrosion resistant designs that we have to put up. Obviously, fatigue is there because it is a much longer design life than the standard AASHTO, which is 75 years. And we had to take into consideration all the replacement of the other elements, which, as Guy mentioned, anywhere between 15 to 65 years. But the key is to come up with a maintenance program and maintenance access plan that provides for those replacements. One of the key elements, as I mentioned, was the 38-month from notice to proceed. And while it sounds like it's 48 months, it's actually a little bit less than that when you take into consideration that in winter, there's about 3 months of very cold weather and very difficult environment to actually do any significant construction. So we had to take that into consideration because for all practical purposes, you have probably about 6 months that you have very inefficient work in it during those winter closures. There's the accelerated bridge construction was the key to how we approached it as a design builder, and obviously looking at the quality requirements to address the performance. In terms of site-specific hazards, seismic, Guy went into details with that. Yes, Montreal is a seismic zone, but it's not a high seismic zone. And in this regard, the wind winded up being the component that governed a lot of the key components in terms of lateral loading. But there's also the very, very wide range of temperature between very cold temperatures in winter and very hot summers in Montreal that actually gave design demands in the longitudinal direction for the pinned piers in the approach structure. Vessel collision, as you can see, you're on a river and you've got a lot of traffic there. A scour, it's a high, a current moving there, and obviously with regards to the ice. Two components were also there, which with regards to the bridge protection, durability to address the 125-year design life, and obviously bridge protection as is done on all major bridges in North America. Start with the substructure or subsurface conditions. There are some good news for on that regard. The bridge is founded on reasonably competent rock, which is not very deep. And that was a good thing, as the boreholes showed. And we took full advantage of that. And I'll go into the design of the foundation in that regard. I mentioned the seismic active region. We took that and we established based on the boreholes and to establish the seismic hazard specifically for the bridge project. So what you see here on the bottom left is the design spectra. For those who design for earthquakes, they can easily tell that this is a rather smaller demand. When you look at the peak accelerations close to where the period is close to zero, it's about a half of the gravity. And that's by and large about smaller earthquake levels. And what's most important is to look at the actual design that we've looked at, where when you look at the cable stay bridge fundamental period at the 4-second range, you're really looking at smaller response spectrum, and same thing applies to a lesser degree on the approach structures. We took full advantage of that in our design, because we recognize that, as Guy mentioned, the performance criteria does require you to design essentially elastic structure, which was in this case something that the structure was going to be capable of taking without really additional quantities, if you will, just because the wind loads and other loads conditions govern the design. What you see on the right side is our time history analysis that we performed, and we took the wave incoherency and wave passage to account for that. So for all practical purposes, the bridge is long enough that one earthquake would occur with a wave when it reaches, for example, the tower of the cable stay bridge. You could have as much as 1 second delay when it reaches the end of the bridge on the other side and the shore. This shows a depiction of the model that was done in Adina to run the global analysis of the bridge. Nonlinear time history was used. Since we were basically essentially elastic, there was no reason to account for nonlinearity of material. However, we did incorporate the depth varying ground motions on the foundations to account for that. What you see here is liquefaction. We can design the structure for the carrying the loads. However, if the ground around it is going to be subject to liquefaction and lateral spreading, you are going to have to take into consideration the down drag that comes from that. And there were two areas on the project. What you see here is next to the existing dike, where the existing dike separates the seaway from the river. And that's the area which had liquefiable soils underneath the dike, which was something that we wanted to make sure that we account for in the global analysis that we did. For wind, as I mentioned, it wound up being a governing load case. So it was very important for us to look at the historic peak gust winds in the airport measurements, and from that establish wind criteria. And what you see on the bottom right are wind loads that were there, and most specifically, a 41 meter per second during construction for stability, and another for a 48 meters per second for a final stability check. And the design was based on 33 meters per second wind speeds. We did two different wind tunnel tests. One was a section model, which was done at West Wind Laboratories in California. Scale was 1 to 50. And basically, as you can see on the right image, the traffic was modeled with a lot of trucks or buses to account for that on the performance of the bridge. And what we found out, the deck was very stable for winds up to 70 meters per second, well above the 48 meter per second required. Now, I should say that this is related to the cable stay bridge, because obviously wind stability is not a concern for structures which are like girder structures and the approach structure. One of the key components that we know in bridge engineering is that a dual box girder, which is interconnected with these cross beams, as you see in the image on the right side, would actually help in the stability, because it provides like vents when the wind is blowing and separates at the box girder above it and below it, and those vents provide for venting. For all practical purposes, the best way to think about it, you do not want the bridge to act like a wing on a plane where it actually gets very much excited. You want to have those vents in there to basically glide through. The aeroelastic model was 1 to 150, and it captured the bridge during construction. The most critical case is right before closure was tested. And we also tested the condition of the bridge with the existing bridge in there, the truss bridge, and without it, to make sure that the bridge was essentially stable. After we did that, we found out that the bridge is stable against vortex shedding, which is very important for comfort of users, traffic, as well as pedestrian. The project does have a multi-use pathway on it with bikers and pedestrians, as well as no concerns with flutter instability. And from that, we captured the buffeting loads for which we designed the bridge for. What you see here is the vessel collision evaluation that we did, which is first and foremost, we start with the fact that the bridge was classified as a critical bridge. We designed for the vessel impact on the St. Lawrence Seaway, and we looked at minimum collision forces from drifting empty hopper barge. What you see on the bottom left is the hovercraft, which basically winded up the vessel that governed most of the design of the river structure, which is the approach. As you can see, there's a zone B where the navigation is expected, which the speeds were supposed to be about 40 knots. And then for the rest of it, it was 26 knots in that regard. We used probabilistic approach, and we made sure that the critical probability of collapse is 1 in 10,000 years. The maximum concentrated load was about 9.5 meganewton at piers 18 and 16, as I mentioned, with the minimum being at 4.5 meganewtons. It did wind up governing, in some cases, the vessel collision, the design of the foundations, and some of the locations. So that was very important for us to establish a true evaluation of the forces. The fact that there was a seaway, obviously, on the right bottom image where you see the elevation view, you can see that that's a very protected area where all the vessels are going there. And since we had no piers in the seaway, we did not have these major forces from vessel collision on the structure. We had to look at scour as well. We looked at the probability of exceedance of 2% and 1%, and we performed hydrodynamic analysis of the area. And from there, we looked at the effects on scour, and those varied anywhere between 3 or about 4 meters to 5 meters in essence. However, scour really was not that much of a problem because our design of the foundations was such that we need to reach competent rock anyway, and therefore most of our foundations were supported on competent rock, and scour did not really come into play. Ice loading is a big issue. The river practically freezes over. The image on the right side gives you a perspective of it. There are several forces that we would design for. One is the dynamic ice forces that would come from collision of ice flows. The second one is static ice flows, where there is thermal movements, just the ice is not really cracking or moving, but it's more like an actual expansion, which is forcing forces on the foundations. There's obviously ice adhesion forces that actually act there, and most importantly at the bottom is the ice abrasion on the piers to make sure that the piers will have the ability to resist the abrasion of the ice for 125 years without reaching the structural components and of the piers. We looked at 30-year records, measured ice thickness. The thickness of the ice shelf was about 1 meter. That was taken into the analysis, and the peak is about late February, early March. Durability was key component of the design of the structure. We looked at it from the onset of design, took it into construction, and ultimately into operations. So for all practical purposes, it was a holistic durability plan where we looked at how we can satisfy the performance criteria set forth by the owner to make sure that we satisfy it. And in some cases, it was about improving on the design material and using stainless steel, increasing the covers. In some other areas, it was about taking construction means and methods into consideration and finding out that there are different solutions that come into place, but most importantly, to come back to the maintenance and what's required in terms of inspection and future replacement and repairs requirements. So for all practical purposes, life cycle modeling is very much like a lot of the things we do in school, where we look at demand versus capacity. Your demands on one side are the de-icing salts that Guy talked about, where you have these salts applied to the deck, and if you don't have proper drainage, those make it into the bottom areas of the superstructure and could ultimately make it into the piers. So that's the demand side. And the capacity side is your material that you're using. If it is a material with high performance mixes with silica fumes and fly ash, you could wind up investing in your concrete mix to improve your susceptibility to permeability of chlorides. And certainly you could use stainless steel bars or calcium nitrate inhibitors or galvanized steel rebar to improve the behavior of your rebar. with the objective at the end of it to make sure that your capacity is such that it exceeds the demands over 125 years. A probabilistic approach was used, as Guy mentioned, and we used stadium modeling to estimate the time to corrosion initiation. I want to make sure that people recognize that it is not to reach any corrosion halfway through or something is corroded. The bridge is designed such that initiation of corrosion doesn't happen until 125 years. The graphs on the right side show that. The image in red shows the corrosion initiation shown with the vertical orange line and the horizontal orange line, and that's where the probabilistic approach, which varies with 10% increments of the various variables, be it the capacity or the exposure of the components to reach that. And we did that for the deck. We did that for the superstructure steel. We did that for the concrete piers, and we did that for the foundations. Last but not least is the bridge protection risk assessment. I'm not going to go into these details. I'm sure you know why, but it has 5 basic components to it, where we work with defining the design basis threat. After that, we identify vulnerable locations on the bridge. Then we look at credible threat scenarios for which we would ultimately conduct a threat analysis. And from that, we come up with a design-specific mitigation of hardening or strengthening, etc. This approach is done right now on all major bridges in North America, and this is no different. We also have an integrated physical, electronic security system, which is basically monitoring the bridge. It's primarily for vehicular traffic to report an accident or report a problem. But obviously, those analytics can be ultimately all used to help with monitoring any activity that is not acceptable. From that perspective, it gives us the ability to react quickly to fire and any security threats. The design for accelerated bridge construction was key to the success of the team. Guy mentioned 48 months. I want to repeat that so that folks recognize that that is a very, very fast schedule. And in my 30 years of experience, I have not seen a project go through that successfully. And this is really a testimony to the hard work of all parties involved. But the key to it all started with thinking, how can we build the project, continue building the project during the harsh winters? And therefore, it was about trying to maximize use of modular construction, where you're practically using either precast concrete elements, which are built in shops, where you have elements that are match cast, or you use prefabricated steel elements, where you're actually doing all the fabrication and matching 3 segments in a row to make sure that all the bolting works, and limit any connection of steel to no welding, because as you all know, in very cold weathers, preheat and post-heat can cause a lot of problems with welding. The second thing is to look at optimizing the span length of the approaches. We knew that we did not have a lot of flexibility from the definition drawings in terms of what you may or may not do as far as span arrangements. However, for the approach, it did allow us a broad picture on that. And we wanted to take full advantage of that, because what you're looking for is reduction of number of foundations versus a longer span on the approach. And I'll talk some more about that. At the end of it, I kind of, when I give some lectures on this to folks that are non-engineers, I tell them the best way to think about it is that we really looked at building the bridge like a Lego set, giant Lego set, where our cranes are getting those pieces, and those pieces are match cast, that they fit perfectly, and you could do it summer or winter, it doesn't really matter. So one of the key components of optimizing the span length was to really look at what Guy mentioned, which was that a concrete depth, a concrete box girder with constant depths would probably have about a 60-meter span, where it's very efficient and very effective, and that would lead to about 50 piers, which are in the marine environment. If we go to a steel option, where you are using an orthotropic steel box girder, you could reach about 100-meter span, maybe a little bit longer, and obviously you would wind up cutting the number of piers significantly to about 30 piers. However, that can be costly, because fabrication orthotropic decks can be take a lot of time, and actually experience shows us that just simply getting up to speed and starting to fabrication these pieces could take about up to 2 years. That's about 24 months. So composite option was what was chosen, which was a concrete deck with a steel tub. In fact, it was two tubs interconnected with a cover plate in the middle. And that gave us an 80 to 84 meter span with 37 piers. It was the sweet spot, which proved to be very efficient and ultimately got the design team to be the preferred bidder on that, or the design builder. So the west approach is comprised of 4 frames. As we mentioned, the typical span is about 80 meters. And the east approach is comprised of 2 frames with, again, a typical span of 84 meters. However, there is a one span, which is about 109 meters over Route 132. What you see here is the superstructure. I want to point you to the middle box. If you look at the left side where it says northbound, or the right side where it says southbound, in the middle cell where there are the 2 diagonals, and inside in there, it looks like a third box. Actually, it's just a cover plate. It's actually a twin box girder system that's there. And really, that was driven by satisfying the definition drawings, which wanted to see a true a closed section of the structure. This allowed the erection of the approach structure in a very easy way, because when you divide the twin structure into, or a box girder, you divide it into 2 twin boxes. You can lift 1 box at a time, and thereby having something with the order of about 80 tons to lift those steel boxes into place. What you see here is the construction sequence, where one pier segment is lifted first, followed by the girder segment with the cranes, followed by the rest. And then after that, you come back with the concrete deck and you do the stitches. The approach had a total of 33 piers, 25 on the west, 8 on the east. The foundations were primarily cast in place spread footings, and there are 19 precast marine foundations on the west, and on the east there are 4 cast in place spread footings with 4 pile caps with 8 cast and drilled holes. On the cable stay bridge, similar approach, but in there we had to use, for the most part, the foundations that are supported on cast in CIDH piles, as we call them, because the soils there were poorer. What you see here is a heavy lift foundation setting, which basically developed by Sarins, a subcontractor on the team. The lift weights were anywhere between 600 to 1,000 metric tons, special purpose, custom built. It took 2 to 3 days per foundation to bring in these 38 marine foundations into place, each one, and set it into place. Very fast, very efficient system, proved to be a key component to achieving the schedule. This image shows the structure again, and now that's the same image that Guy mentioned. However, this image here is shown of what the design builder is developing, and I bet you can find very little ability to tell the difference between the two. The pier bends are, as Guy mentioned, it's not what a structural engineer would look at to develop first thing. It really is trying very hard to support the superstructure. However, it is, I've learned to like it. It's a beautiful, elegant pier structure, but it definitely had its challenges in terms of coming up with a way to design it and ultimately build it. The inclination of the piers was difficult, and obviously those W frames you see at the top that are connected were very difficult to design. We've looked at them made out of concrete, we looked at them made out of composite, and we looked at them made out of steel. And at the end of it, we chose steel for the steel portion at the top for that bent. The pier themselves were done with precast segment pieces, which are all done in the shop, match cast, and built that way. We used different concrete properties. As I mentioned, it was primarily driven by the durability. However, obviously design had a lot to say about that, because we obviously want to minimize the weight. So for example, the deck slabs on the cable stay bridge used 70 MPa high strength concrete. The deck slabs on the approach were 60, and the pylon shafts were in the order of 60 megapascals. But this is all important to design ahead of time, because obviously all of these impact your overall design as you proceed with your works. What you see here is an image on the bottom left where the precast shop is, where the segments of the piers are being fabricated there, match cast. And on the right side, you see the piers being erected, and you see those grout stitches as you are placing one segment over another. This is another image during construction. And high here, what we see is the steel pier cap being lifted. That's about a 200-ton segment, fabricated in Spain, shipped over the Pacific, and lifted. As you erect these pieces, which are all fabricated and matched in the shop, when you come to the field, you know that very little tilt as you connect the steel pier caps to the top of the piers, you can wind up with a large differential at that connection at the center line splice. What we opted to do was to provide the contractor with a detail, which is shown on the bottom right, which is a pre-stressed tendons or rods, basically grouted, creating a composite connection, which allowed for slight, half an inch differential between the left and the right pier cap pieces, the V sections, and still be able to make that structural connection. On the cable stay bridge, what we see here is something that was very clearly defined on the definition drawings. So we followed the span layout. However, what was done was to look very carefully at the concrete of the tower itself and what kind of material it will be made for, and sure enough, to also look at the superstructure and decide on what to do. So we looked at multiple options, the back span being made out of concrete, to make it out of composite with concrete infill to counterbalance it. And the main span, we looked at orthotropic steel box girders, as well as composite sections. And at the end of it, when we looked at the whole thing, the solution that made most sense is to go with a composite solution, very similar to what we did on the approach structure with the back span, the 124 meter, using some counterweight to basically balance the tower equally. For the main span, we used post-tension cast-in-place footing with CIDH piles. The lower shafts were inclined and also used precast concrete segments. The upper shaft used cast-in-place concrete, and the shafts were braced in the middle with the lower crossbeam, as well as the upper precast was connected with the bow tie. Here, what we see is a typical precast segment, 77 metric tons. It's hollow and stacked one on top of each other, and it's post-tensioned. The joint remain in compression under the service loads for the duration of the design life of the bridge. Here you see the precast segments being lifted into place. We practically lifted 44 precast the lower 44 precast segments, and it took about 3 to 4 segments erected per day, and we completed the whole job in 40 days. The MST lower shafts and the epoxy joint mock-up is not just limited to the MST. It happened for the main span tower first because it was the one that started being built first. However, it applied for the whole piers as well, which all had the same epoxy joint that was done. A very clear mock-up. A mock-up was done. Very important in terms of the quality control. I talked about the durability and the importance of looking at the construction piece, because you can do all the durability analysis. If the pieces are not constructed to the specifications required in the design, you are not going to have a structure that's going to last like you design it. So it was very important to do it, and we did a pressure test where the pressure was kept for 5 minutes without any loss in the pressure, and that was following the PTI recommendations. Later on, we drilled cores at 45 degrees and showed that the epoxy on all surfaces is intact, and the samples were also tested for strength. The MST upper shafts were cast in place. There was 15 cast in place segments, and it took for every lift about 2 weeks with jump forms to complete the tower. The anchor, the saddles or the link beams in the tower was a unique design. It was designed as a composite, which is integral part of the tower segments. it was such that the independent anchorages are outside the tower, and then it allows for modular construction. What you see here in the image in the middle is an actual integrated shop drawings, which models every rebar, every PT, every sear stud to make sure that everything fits. And on top of that, we include the actual temporary frame that's going to be buried inside the tower shaft that is going to hold the structure together to construct it. That was all done on paper in the computer to avoid clash detection, and ultimately went to the field, and the images on the right side sees the pieces being built. This initial investment saved a lot of issues during construction and fabrication. The stay cables work the hardest on this project. I tend to say that the design was kind of pushed to its limits in that regard. We winded up using the maximum number of strands that we can fit, 127 strands, and the construction of the cable stay bridge had to be tweaked very carefully so that we don't exceed the stresses during construction of the cable stay bridge. The supplier was DSI. The strands were galvanized wire strands with wax and polyethylene coating, and followed by HDPE pipe sheathing, and basically a watertight anchorage zone. All stays of major cable stay bridges require a damping, and every stay included a twin tube with hydraulic telescope dampers for vibration control. These are basically tuned to avoid vortex shedding and rain-induced vibrations, as well as galloping due to the inclination and wake galloping. The excitation from vibrations from other parts of the bridge was also included. So it was a rather comprehensive evaluation to make sure that these stays last the 65 years that we're intended for. One of the key components of building stay-supported or cable-supported bridges in the Northern Hemisphere is a lesson that we saw on the Portman Bridge, where some ice pieces fell from the stay cables onto traveling public once the ice storm ends and some warmer weather hits, and then it melts, and then they fall onto traffic. So one of the key components was to have these stays be away and not above the traffic. However, we all know that these are very high, and in wind environment, when even it falls, it's not going to fall perfectly vertical. There's a good chance that it still will act. So the requirements and the performance criteria was to come up with a method of reducing that hazard. And we did quite a bit of testing to evaluate optimize on the actual helix design that is usually used on these stays to reduce the wind vibrations or rain-induced vibrations. And we found out that if we change the helix on a stay to a actual ring, and the ring spacing is reduced to 300 millimeters, we actually by default wind up having the ice accretion reduced in size, such that these pieces, if they fall, they're no more larger than your hand, or maybe a little bit larger, but they're very small pieces that ultimately are no danger to traveling public at that point. The superstructure looks very similar to the approach structure. The difference is that it is a true box girder. It works very hard. I tell people that the cable stay bridge in the signature bridge works harder transversely than it works longitudinally. If you look at the bottom image where the stays are, the cantilever portion on either side, to the left or the right, is practically a cantilever bridge, and you have to design for those loads. So basically the top deck is in tension transversely, and the bottom portion of the box is in compression. We use different structural steels. What's important is to know that we used high performance steel where it's needed to reduce the weight of the superstructure. This shows some of the fabrication that was being done in Spain. These segments, as I mentioned, it's a huge arena there, which basically was used to cover it from the sunlight so that you can, match these pieces and make all the measurements that are needed without having to worry about when you do it at which time of the day, because if you put it in direct sunlight, it impacts the geometry control that is needed. What you see here is another key component, which is the precast deck panels. In all The deck panel was all comprised of duplex stainless steel, which was specified by the owner in this case. The number of panels were 1,400 for the cable stay bridge and just close to 10,000 for a total for the approach. We had multiple shops doing that. The northbound and southbound were working with 5 casting lines, and the transit corridor were working with 3 casting lines, and we were producing up to 50 panels per week. This shows an image of when you place the precasting panels in place and all that overlap of the reinforcement there with the shear studs underneath them was all carefully designed so that the placement can work. And then ultimately you come back with a stitch pour to make the full deck composite with the steel. What you see here is the king post of the tower using another accelerated approach that we had to use. As we were constructing the bridge, we were challenged with some few unforeseen events. And at one point, we decided with the contractor that it's probably better to move the closure pour of the cable stay bridge, which was on the critical path for bridge opening, instead of matching at the end of the pier, or MS-15 as we call it, at the end, we actually chose to start building from the other side using this king post that you see in red, and to make the closure segment as MS-11, thereby basically building from both sides. And the image I'll show in a little bit will clarify this further. What you see here is a typical construction of one of the segments. As we lift it, we bring it to underneath the tower and lift it up to place and use a gantry, dynamic lifting frame, to take it into place. This is the delta frame that was used to support the segments as you are building them without any support of the stays. And then as you build the segments one by one, these are 800-ton pieces built into place. And there's a video that I'll show at the end that will depict that a little bit. There was a very strong requirement of the seaway restriction zone, which we are going to start building over at this image, which required the contractor not to do any construction when there is seaway traffic in summers. So while the problem was in winter, we have very difficult and inefficient ability to construct. During summer, the seaway needs to make sure that we have no construction over them in any significant way. So again, the use of large modular segments of 800 tons lifted into place was the way we chose. Now, as you go with this and you erect it, you can see here on the right side, we actually, instead of continuing from the left and finishing up the closure all the way to where Pier E01 is, which was segment 15, we actually at one point, because to accelerate the schedule, chose to build the king post, and we started building another mini cable stay bridge from the other side to make the connection in the middle and achieve the schedule we wanted. Obviously, all the red is temporary works that got removed later, and we finished the bridge on time. This is a global team. It took a global team to finish this international project. Quite frankly, a very, very substantial undertaking by Montreal and Canada and Quebec. It took work from primarily a lot of folks from Europe, a lot of folks from the North America, but ultimately what it required us to do is to have a place where we all can have all our documents in one place, and anybody could upload or download and work remotely. So what's interesting is that we have been doing that. We were doing it prior to COVID as engineers on projects such as this. And when COVID hit, here I am presenting to you from San Francisco, and we all know that we've all worked in this environment before. So it's kind of a testimony that those kind of big projects trained us to work that way, because that's what was needed a long time ago prior to COVID. Effective communication, as I mentioned, was important. It was a cloud-based environment where everything is there. And I pretty much covered this slide, so I'll skip to the next one. So key takeaways. Guy mentioned a vision which the client wanted to see, which was usually achieved through a design bid build procurement, where the design is completely done and then you ask a contractor to come and build it. However, the project schedule was such that the existing structure was aging and there was a need to accelerate things. By providing these definition design drawings, the owner achieved two things: achieving the innovation that design build allows, or P3 allows, and at the same time still achieve the design that they envisioned. Heavy precast, as I mentioned, and pier foundations was key to our success in achieving the schedule, which was quite frankly very aggressive. This modular joint, as I spoke about, was basically worth the investment in every single way. When we all saw it happen, for the longest time, people were like, what's going on? We don't see anything on the field. There's not a lot of activity. But once it started, boy, it went very fast. There was a use of the sacrificial hydraulic jacks to level the foundations, those very heavy foundations that were lifted into place and lowered. We had sacrificial hydraulic jacks that were used to make sure that we reach the tolerance we need, and that was very successful. Specialized training was required in Quebec for use of stainless steel rebar. That was very important because even simple bar bending winding up being a problem, and we did that head on in the beginning to make sure that it doesn't develop a problem with all the 10,000 plus precast panels for the deck that we needed for construction. Development of the special concrete mixes and performing it hand in hand with a durability design was very good, because we were able to look at the investment in what it takes to get the concrete mix to the level we need to avoid infiltration of chlorides. And last but not least, the environmental protection presented by key challenges, particularly during the aquatic excavation to the rock, and the fitting and the turbidity of the winter conditions was something that we carefully worked around so that it doesn't wind up being an activity that stops and arrests all construction. And that was very important. And the project was targeting an envisioned bronze as a requirement by Canada, but the higher platinum level was achieved by the team under the DBP3 project delivery method, confirming a great success. Credits to the owner, developer, the contractor was Signature on St. Lawrence Construction, a partnership of SNC-Lavalin with Dragados and Flatiron. As mentioned, TY Lin was the managing partner of a joint venture of TY Lin, IBT, and SNC-Lavalin Engineering. The owner engineer is Arup Canada, and independent engineers Stantec and Ramboll. Many sub-consultants contributed to the success of this project, and it's an honor to be part of it. I think what we're going to see here is a brief video that's going to show the construction of the project. This is courtesy of our partner, SNC-Lavalin, who prepared it. So I'll let it play.
So we opted for a modular construction strategy, essentially taking the full bridge and breaking it out into Lego-sized blocks. So it's really a question of speed. So when you're prefabricating pier segments or fabricating steel elements offsite in a factory or in a shop, well, you get a better component.
Overall, we have 1,300 pieces that are deemed oversized. There's three main categories. The first one being the pier segment and the pylon segment. So those are concrete pieces, and there's about 360 of those. Then we continue with the pier cap and the superstructure, which include about 304 pieces, mainly coming from Spain. Finally, we have the steel girders, and there's 601 of those. Depending on the origin and destination of these pieces, we go from one mode of transport to the three modes of transport. The reality of Quebec is we have the winter, we have changing temperature, and we have a lot of change coming through the year. So we're constantly communicating, working with the rest of the construction team to ensure a smooth delivery of each of the pieces.
Operating on the river involves essentially working on maritime barges. The river itself is very wide, not very deep, a very strong current, strong winds.
Mother Nature plays a huge role in anything we do here on the water. We constantly have to monitor the wind speed as well as the speed of the river. And then during the winter, we had to constantly monitor the ice flow flowing down the river, which increased the risk of any water operations we were doing.
In order to complete those complex activities over the highway, we had to work during night shifts and during full weekend closures.
All this involves many complex operations tasks. So one of the first things we need to do is to actually do a risk analysis. Why? Because in the bottom line of all of this is health and safety is priority one on this project.
The cofferdam allows the workers to safely enter and construct the foundation footings.
It's here on the West Jetty. We fabricate 38 out of 74 footing and pier starter that will be installed on the rock at the bottom of the river. On top of these footings, then we build a pier starter, which will allow us to emerge out of the river. And then, on top of these pier starter, we will stack the prefab element that will constitute the pylon of the bridge or the pier leg.
The first step is to prepare the riverbed of the St. Lawrence River to receive the footing. We have prepared a barge with an excavator that excavates the overburden and the rock to a depth of about 5 to 10 meters from the top of water.
Each pier varies from 3 to 8 segments, weighing each at 65 to 70 tons. The highest pier closest to the cable stay bridge has a height of 35 meters. The pier caps are the 2 V sections that are connected in the middle. They allow to transfer the load from the superstructure to the pier legs. We have 37 pier caps on the new Champlain Bridge, and each pier cap weighs around 400 tons.
All box girders and deck slabs are fabricated off-site. On the 3.4 kilometer bridge, we have over 600 box girders and over 9,600 deck slabs. The box girders are steel components which are supporting the weight of the concrete deck, and that's where the road circulation goes.
The cable stayed section of the new Champlain Bridge is definitely the landmark of the future bridge. The main tower of the cable stayed section will culminate at 170 meters above the river. This section will be slightly more than 500 meters long and is located more or less in the middle of the bridge, which overall will measure 3.4 kilometers. The foundation of the main tower are a series of 42 drill shafts, which have been drilled 10 meters into the rock and which anchor the foundation of the pylon, which is made of 2 hull caps of about 950 cubic meters each. The tower heads, the top section of the pylon, will be cast in place by 6-meter high lifts. The deck, backspan and main span are suspended to the pylon via the stay cables, so the main span and the backspan are balanced and hanging from the main pylon. On this bridge, the segments are 60 meters wide, 12.5 meters long, and each of the segments weigh around about 850 tons.
The MLB is the one that lifts the segment from the ground level to the bottom of the deck. The second element is the trolley that transports the segment under the deck. The third system is the one that erects the segments from under the bridge to the final position.
The main span of the cable stayed section has to be built without encroaching on the seaway channel at all. We were faced with an incalculable amount of challenges, but every single one of them has been solved, and the result speaks for itself. I'm extremely proud to be involved on such a project, which is once in a lifetime opportunity for most of us.
Thank you. At this time, we're going to take questions. So Shaunak is going to moderate that. He's going to, I know we've got some questions come in from the Zoom. And if anybody has a question here, please just step forward. We got microphones at the end of each aisle. And Marwan's on the screen, and he is here. So I guess you want to start with a...
Sure, yeah, I'll get started with one of the questions that was submitted online. With the expansion joint number being reduced to 7, how much movement did the design team need to account for given the long spans and seismic requirements? Also, what other challenges were encountered as part of the decision to reduce the number of expansion joints?
I think I can answer that, Marwan. If I make a mistake, you can correct me, but I think total when the factored movements, I think we're up talking about a meter movement. I think that one of the largest joints has like 10 modules or something like that. So that's the order of, so yes, so it's significant movement at the expansion joints.
Do we have any
the thermal movements were one thing to deal with, but the other one is when we have the pinned piers on the frames, they were subject to large thermal forces due to contraction and expansion. So that was another challenge with limiting the number of expansion joints.
I'd like to ask a short question. Maybe I missed seeing it. Your pier, support for piers, the column is inclined outward, right? And that supports rests on the foundation pads with a pile. I didn't see any horizontal element to tie the two together. Is it because horizontal force component was small enough you can depend on the flexure stiffness of a pile or something? How do you take care of that horizontal component?
I can take that, Guy. You're very perceptive. The question is very valid. I noticed in the video that was presented for the tower, the pylon, MST as we call it, it showed the piles underneath each leg, but it did not show the horizontal tie that is there. In fact, there is a horizontal tie, two ties that connect the pier caps, and they are actually horizontally pre-stressed. Now that is for the pre-stressed, that is for the MST, for the signature or cable stay bridge. For the other piers, the force in itself was such that it is something that the pier and the foundation can resist the lateral force by friction, and it doesn't govern the load. And another thing we did is we actually supported the pier eccentrically on the mat foundations so that the forces are balanced, if you will, as far as a total overturning. So two things what happened on the piers themselves. There was no need for a horizontal tie because the forces are small. And at the same time, we economized on the design of the foundations there by putting the pier eccentric a little bit. And on the main span tower, there is indeed a horizontal tie that connects the foundations of each shaft.
Thank you. I have another almost unthinkable question. You know, world today is so much extremism, geopolitical and social, cultural, whatever you name it. And the last few weeks, early this month, we were exposed to so many of the pictures of the World Center attack. So my question is, do you give any security consideration as to how to prevent such an attack for such a major structure?
I can take that one, Marwan. It's a very good question. Unfortunately, we can't go into any details on that, but certainly it was those aspects of it were considered. I know Marwan touched on it a bit, but there was some degree of hardening, and there's an entire security-related aspect to the project. That was one of the challenges in doing that because we can't divulge too much information, but at the same time, we got to get people that are highly specialized in the area to work on the project. So yes, it was accounted for, but we can't go into any detail.
I could add
to
the fact,
Marwan.
Yes, I could add to the fact that very similar to this earthquake zone, you actually of making sure that there's nothing that is determinate or something that, for lack of a better word, is vulnerable and robust. You want to make sure that your design is robust. You want to make sure that there's multiple load paths, and you want to make sure that certain vulnerable areas are reinforced with minimum investment that improves the behavior significantly. So those are things, that's the general approach of it in terms of how we approached it. Certainly, unfortunately, we cannot go into the details of it.
Thank you. I think we have time for one last question. There's been a couple questions in regard to the reinforcement in the deck. Was any type of FRP material considered in lieu of stainless steel?
Yeah, I can take that one, Marwan, if you want. The deck slab itself is all entirely stainless steel, solid stainless steel. As I said, we are converting for a light rail system, and on the light rail system, we were worried about stray currents because we will have an electrified system. So all the plinths that are being anchored into the deck, they're all glass fiber reinforced polymer to mitigate, conducting electricity through the rail into the deck. So that has been a challenge, and we made the decision to go with the glass fiber reinforced polymer for that. And it's been working well, getting a good supply of the material. They're quite a large quantity to be used, but we were able to, and we did some, Marwan's team did some special investigation because of developing the shear friction of that element. Has some challenges, but so that, yeah, we did adopt that for those components.
Thank you both. I'm sure we could ask you a million more questions about these, but I'm going to hand it over to Greg and Santiago for some closing remarks.
I would just like to mention that I have a small gift for Paul Zia, Dr. Gilligan, and Dr. Balaz. It's the Royal Canadian Mint issued a commemorative coin as part of the opening day celebrations, and so I have 3 of them here. So I'd be pleased to hand those over to you at the end of the session.
Thank you. Yeah, thank you both so much. Marwan, I don't know if you can still hear us here, but thank you very much for joining us today, and Guy, thank you for taking your time to join us.
Thank you for the invitation. I really appreciate the invitation, and I'm sorry I couldn't make it in person. I was looking forward to that.
Great.
All right. On behalf of everybody in the committee, I want to thank you very much for attending today's lecture. As a reminder, PDA certificates and a survey is going to be distributed to everybody who attended this event via email. And now, at this time, I want to introduce our 2022 topic for the Paul Zia Distinguished Lecture, which is the Rainier Square redevelopment in Seattle, Washington. Ron Klemenczyk, Chairman and CEO of Magnusson Klemenczyk Associates, and Dr. Amit Varma at Purdue University will be presenting on the design and construction of this iconic high-rise building located in downtown Seattle. Please mark your calendars for the fall of 2022 for the 21st annual Paul Zia Lecture. Again, thank you for attending today, and we hope to see you all in person on next fall as we continue this great tradition. Thank you.